This is the third and final part of the 16th lesson in heat transfer. This lesson has focused on introducing what convection heat transfer analysis is all about, emphasizing that fluid mechanics plays a critical role in analyzing convection heat transfer. In the last lesson, we were shown what the concept of the boundary layer is. In this lesson, we will take a deeper look into how we calculate the thickness of a boundary layer. These calculations will help us to understand how boundary layers grow. By the end of this lesson, you should be able to calculate the thickness of a laminar boundary layer, a boundary layer tripped into turbulence, or a mixed boundary layer. You should also be able to describe the mechanism associated with transport of momentum and thermal energy in laminar and turbulent boundary layers. On with the lesson. We saw in the previous lesson that the Reynolds number plays a critical role in predicting the thickness of laminar and turbulent boundary layers. Let's review what the Reynolds number is. The Reynolds number is a dimensionless grouping of variables. It is often calculated using the kinematic viscosity of the fluid, which is denoted by the variable nu. In the definition of the Reynolds number, U with a sub-infinity denotes the velocity of the fluid in the free stream, far away from the boundary layer, where the effect of the object over which the fluid is flowing has not been felt by the fluid. The velocity is often denoted in meters per second. The variable x denotes the distance from the leading edge of the flat plate. Nu is the fluid kinematic viscosity. The kinematic viscosity of a fluid has the units of length squared per time, often denoted meters squared per second. The fluid kinematic viscosity can be calculated from the fluid dynamic viscosity and the fluid density. The fluid kinematic viscosity is defined as the ratio of the fluid dynamic viscosity and the fluid density. The fluid density is denoted by the variable rho. The fluid dynamic viscosity is denoted by the variable mu. Fluid density has units of kilogram per cubic meter, mass per volume. The fluid dynamic viscosity is often reported in units of Newton second per meter. An equivalent set of units is kilogram per meter second. To calculate the Reynolds number, one uses the free stream velocity, the fluid kinematic viscosity, calculated at the film temperature of the fluid, and the distance from the leading edge of the plate x. The film temperature is the average temperature between the fluid in the free stream and the fluid surface at the surface of the plate, whatever the plate temperature is. When we substitute in the definition for the fluid kinematic viscosity, we can also see that the Reynolds number is calculated as the product of the density, free stream velocity, and the distance from the leading edge of the plate x divided by the fluid dynamic viscosity mu. To calculate the thickness of a laminar boundary layer, we use the analytical solution produced by Blausius, who is a student of Ludwig Prandtl. The thickness of a laminar boundary layer can be calculated as 5 times the distance from the leading edge of the plate divided by the square root of the local Reynolds number. This laminar boundary layer thickness is defined as the distance required for the fluid to achieve 99% of its value in the free stream. Let's think about how a fluid flows in a laminar boundary layer. Imagine a box surrounding a packet of fluid molecules. Upstream of the plate, the box looks like a square. We will now imagine what happens as the fluid in this box flows along its path into the boundary layer. Once the packet of fluid has moved into the boundary layer, the plate begins to slow the fluid down at its surface, such that the fluid molecules at the bottom of the square begin to flow slower than the fluid molecules at the top of the square. This causes the square to change its shape and move from a square into a parallelogram. The area of the square, however, is not changed, as mass must be conserved. As the fluid packet continues to flow downstream, the effect of the boundary layer is to continue to slow fluid down near the plate, which stretches out the parallelogram, as shown here. The question is, how does the fluid slow down? If you recall that at the microscopic level, the fluid is made up of a number of different molecules that are randomly moving around inside of the box. Even though the fluid has net motion down the plate, if we were to move with the fluid, we would just see the fluid molecules bouncing around. Some of the fluid molecules in the square randomly move out of the square. When they do so, and they encounter slower moving fluids, particles below the square, these molecules collide and exchange their momentum. The slower moving molecules closer to the plate slow down the molecules above it. The faster moving molecules farther away from the plate collide with the slower moving molecules near the plate and speed those molecules up. This random motion at the molecular level, causing the fast-moving molecules to move down and meet the slow-moving molecules, and the slow-moving molecules to move up and meet the fast-moving molecules, is the mechanism by which the fluid is slowed down as it flows over the flat plate. We say that this transport is dominated by molecular diffusion. Molecular diffusion causes the spread of a deficit in momentum in the fluid. Molecular diffusion will also be the mechanism by which thermal energy is transported away from or towards the plate. In a turbulent boundary layer, the flow looks very different. Imagine that the boundary layer is tripped at the leading edge to become turbulent immediately. This can be accomplished by adding elements that stir the fluid up near the leading edge. In a turbulent boundary layer, additional motion is achieved in the vertical direction due to swirling eddies. These eddies vary in size, vary in their direction, and are inherently unsteady. The turbulent flow is thus three-dimensional and unsteady. The swirling motion of the eddies causes mixing of the fluid in the boundary layer. We can again imagine how a packet of fluid molecules approaching the flat plate will move through the boundary layer. Here we have our square packet of fluids. However, now they move through the boundary layer much differently. Immediately upon entering the turbulent boundary layer, the square will become distorted and initially will take on the shape of a horseshoe as the mixing rapidly causes the fluid molecules to move in all directions. After after time in the boundary layer, the organization of the fluid particles will be completely indistinguishable, as the fluid particles in the original square are mixed over the boundary layer. This mixing is what is characteristic of turbulent flow. Transport in a turbulent boundary layer is dominated by three-dimensional and unsteady eddy motion, causing the fluid to be mixed up. While there is no exact way to calculate the thickness of a turbulent boundary layer, many experiments have shown that a reasonable approximation is given by the equation here. We will now look and compare how turbulent and laminar boundary layers grow. As one might expect, due to the mixing in turbulent boundary layers, the boundary layer thickness grows more rapidly than in a laminar boundary layer. Here we are imagining a flat plate over which room temperature atmospheric air is flowing with a free stream velocity of 10 meters per second. 10 meters per second is equivalent to 36 kilometers per hour. The air approaches the plate at a uniform velocity. At x equals 0, it encounters the plate surface. Here we are imagining the boundary layer initially growing with the laminar region. Unless there is something added in to the flat plate to cause the boundary layer to become turbulent, all boundary layers begin laminar. There are two regions in this mixed boundary layer: a laminar region and a turbulent region. While in reality the transition from laminar to turbulence occurs over a range of the plate, we imagine for the purposes of this demonstration and in this class for doing calculations that the transition happens at one point. The transition point is calculated using a critical value of the Reynolds number of 5 times 10 to the 5. That is 500,000. For flow of air over the flat plate at 36 kilometers per hour, this transition happens at 0.79 meters away from the leading edge. The thickness of the boundary layer at the point where the boundary layer transitions from laminar to turbulence is 5.6 millimeters. Note the very different changes in scale here. The boundary layer is intentionally shown much thicker than it is in reality for this particular flow condition. This plate is 1.5 meters long, but the thickness of the boundary layer is scaled in millimeters. When the laminar boundary layer transitions to turbulence, it is only 5.6 millimeters thick. This is very thin. In the laminar region, we calculate the thickness of the boundary layer using the Blasius solution. The laminar boundary layer thickness is 5 times the value of x, the distance away from the leading edge, times the Reynolds number evaluated using the length scale x. This is u infinity times x over the kinematic viscosity of air. In the turbulent region, we apply the turbulent boundary layer thickness approximation. Note here, however, that we must use a different length scale parameter, because this equation assumes that the turbulent boundary layer begins growing at x equals 0. This is not the case in a mixed boundary layer, where the boundary layer is initially laminar. If we were to imagine the turbulent boundary layer projected back before the transition point, it would begin growing at some point denoted here. This point is the reference point for the length scale in the turbulent boundary layer equation. We must determine where this is relative to the leading edge of the actual plate. We can calculate this new length parameter for the turbulent boundary layer as the value of x, the actual distance from the leading edge of the plate, minus some change in the starting location. That delta x is the difference between the actual leading edge of the plate and the fictitious, imaginary starting point for the growth of the turbulent boundary layer. One can determine this distance by linking the laminar boundary layer thickness and the turbulent boundary layer thickness at this particular point. The laminar and turbulent boundary layers must be equal at this location, which allows us to determine what the value of this delta x is. When calculating the thickness of mixed boundary layers after the transition point, one must accomplish this matching of the two equations in order to correctly calculate the boundary layer thickness. Let's compare how the mixed boundary layer, the one that begins laminar and then becomes turbulent, grows relative to a boundary layer that is tripped to be turbulent from the leading edge of the plate. Here, the dashed line represents the tripped boundary layer. Remember that in a tripped boundary layer, there is something placed at the leading edge of the plate in order to disturb the flow and cause the flow to be laminar immediately. As one can see, the turbulent boundary layer that has been tripped grows at a much more rapid rate than the mixed boundary layer, which has a leading laminar region. Because the turbulent boundary layer was tripped, we can simply use the value of x in calculating the boundary layer thickness. We do not have to try to match the two boundary layer equations. Due to the mixing in turbulent boundary layers, momentum is transferred more quickly, and they grow more quickly. One might imagine that heat transfer is also faster in turbulent boundary layers due to the mixing, and this is the case. Heat transfer is faster in a turbulent boundary layer than a laminar boundary layer of the same thickness. This is the end of Lesson 16. Hopefully, you have a better understanding of what a boundary layer is, what the thickness of a boundary layer is, and how to calculate that thickness.